Okay, hello everybody. My name is Ben Kropowski. I'm the organizational director for the UNIFI Consortium, and welcome to the next in our spring seminar series. Today we have two guest speakers that are students at the University of California, Berkeley, Jose Daniel Lara and Rodrigo Henriquez. We'll be talking about revisiting power system, time domain simulation method and models, and describing how we can apply some of these techniques to look at grid forming inverter technologies. So I'm going to go ahead and turn this over to you guys. Go ahead and take it away, and we'll have questions at the end.
Okay, thank you, Ben. Yeah, so in this presentation, both of us will be talking. So Jose Daniel will be handling the slides. So we'll do our best to have sort of smooth transitions. So yeah, if you go to the next slide. Okay, yeah, so as a motivation, I guess our discussion started first when we were looking to simulate actually a grid forming inverter, and our supervisor asked us about essentially which technique and which type of model we should use for that simulation, and essentially what type of phenomena matter for running those simulations. And you see, for context, we don't actually have a simulation tool in a research group. So the motivation, of course, was to develop one of our own. And as a student, sort of just starting reading this topic, we're looking to understand what do we need to do to run a simulation with an inverter from the basics, right? So in this case, as a starting point was a inverter against an infinite bus type of model. And we were kind of successful in this, but the challenges, of course, for us started when we're trying to look sort of in a more system-wide, multi-machine, multi-inverter type of simulation. And for us, was like, yeah, this shouldn't be that hard, right? Well, keeping the story short, in the end, after reading a bunch of literature and reading many, many terms that are somewhat present in this word cloud, the question that was interesting for us to understand was when a phasor simulation is the same as an electromagnetic transient or EMT simulation. And as you can see, there is already some language imposed here that we will need to clarify. So Jose, if you go to the next slide. Oh, I think you're muted, Jose.
Yeah, sorry. So as you guys, Rodrigo was noticing, we started developing our own simulation tools, and we suddenly realized that, okay, the electric grid requires simulations as a fundamental tool to test a bunch of assumptions, design controls, and do like analysis. However, from the fundamental side, it wasn't obvious what type of modeling technique was actually able to allow us to answer the questions that we wanted to answer in terms of stability, understanding the effects of the system of different parameters and controls. And it wasn't obvious from the beginning what were the differences and similarities between these simulation techniques, and also some of the novel simulation techniques that are showing up, right? So we had positive sequence, RMS, EMT, phasor. And we even had like a student discussion group with other colleagues over the span of months to try to come up with like what the definition should be. And we decided to take a step back and say, okay, let's stop trying to like guess what things are and go back into which assumptions and simplifications are used in different modeling techniques and which ones are supported by different modeling tools to understand how do these existing techniques and models change with the upcoming changes for IVRs, right? So like, for example, we know that the machine world, if we think about just machines, we have the IEEE 11100, 1110 that tells us how to model machines in different contexts. We didn't have the kind of thing for inverters. So this presentation is trying to looking into how do we understand the requirements to answer questions about different kinds of phenomena when it applies to IVRs and especially grid forming inverters, right? So, we can frame the general motivation of this presentation in terms of this old saying, right? Like all models are wrong, but some are useful. Well, we're trying to figure out how wrong are some models and when they stop being useful to reach engineering valuable conclusions. So the first part of the presentation, we're going to actually try to focus on an overview of what a time domain simulation is in the context of power systems, and the relationship between models, solution methods, the importance of simplifications and transformations to actually be able to obtain valuable insights from the engineering perspective in simulations. And we're going to take a bold step by introducing first our proposed classification and taxonomy of these simulation models, so we can actually frame their limitations and their capabilities.
Yeah, and after that, we'll work more in depth about transformation and simplifications, in particular, how averaging is used in this type of simulation, how we can use dynamic phasors in time domain simulations. Then we will talk about the importance of reference frame transformation in this context, how singular perturbation theory is used here, and we will show an example of how these techniques are used to actually classifying a type of simulation. And finally, we will revisit our proposed classification and taxonomy and talk about the main two categories used. And we'll discuss a little bit more about simulation semantics and those used to describe this type of models. So if you go to the next slide. Yeah. So first of all, I just want to say that this work, it's sort of a compilation of a lot of great engineering work from really famous engineers, such as Herman Dommel, Seth Sanders, John Saborski, Jose Marti, and many, many more, that were the ones that actually formalize most of the stuff that we're presenting here. From the Dommel method to dynamic phasors, a lot of these concepts that we will be talking today are based on their work. So if you go to the next slide.
So like this, let's start with like one of the things that we were realizing as we're looking to this work is like, even though some simulation models can have different capabilities, there was not generic simulation model we can start working from. Most of the papers and most of the contributions about some of the system-wide simulation models start already with certain transformations or certain simplifications applied to them to begin with. So we start this presentation by introducing a very generic simulation model where we have two types of states, X and Y, that are, generally speaking, they could be complex values, and they can also take real values for different type of formulations. And X is the representation of all the states that are like relevant to devices, and Y are the network variables, right? Usually are voltage and currents. In some formulation types, it could be also powers and reactive power, but those are not generally commonly used. And we're gonna frame a lot of this presentation in terms of what are the different treatments that function F for the devices and function G for the network are used, so that we can actually solve simulations. And again, with the perspective of trying to achieve engineering insights, right? Like if we want to go to the extreme, we can think about this model going all the way down to like, the atoms and material science and so on. But we're basically saying, let's start from the frame of an explicit set of differential equations that are time variant, because in the most general case, X and Y can take sinusoidal or sinusoidal form, and focus about how this model gets transformed to achieve different levels of solvability, that, the word that we're kind of like using for this, and also understand how different commercial tools tackle the challenge of actually solving this system of equations in a general form, right? So given the system model we saw before, we can define a time simulation model in the general setup. We have a set of initial conditions at time 0, and we advance from one point to another one in a discrete timeline using an integration algorithm, right? Or a stepping algorithm, if we want to think about it in a much more general sense, right? So we have some devices, synchronous generators, IPRs, loads, and facts. And we highlight here the network, because the network is the part of the modeling approach that creates the largest amount of diversity, because, how do we tackle the network model seems to create a lot of the differentiations about how do we actually solve the model and how we simplify it. So like this generic model could result in an ODE or in a dynamic algebraic equation system. And then we can solve it using explicit methods, implicit methods, or the numerical integration substitution. And we're giving like a special mention to this because the numerical integration substitution is the basis of the Dommel method that, allows us to actually have simulations of, waveform type of models that are like the most detailed ones. So in a sense, the modeling choices that we make about F and G inform the solution technique that actually allows us to find a valid result for that system and the integration choice. And in turn, the integration modeling, so the integration algorithm requirements informs the computational requirements for that practical application.
So yeah, I guess in practice, dynamic simulation models in power systems are often framed in terms of slow and fast. Although it's not necessarily clear what exactly is fast and slow in every case or in every simulation. So those terms are actually contextual or what you're actually studying, right? In the realm of synchronous machine dominated systems, there is somewhat an agreement of what is fast and slow phenomena. The standard IEEE 1110 again does a really good work in providing such classification of what type of model we want to use for which type of phenomena we want to study. However, I guess in the case of inverter-based resources and their associated controller, associated parameters, it's not as straightforward to categorize in which type of simulation and what level of complexity we shall use to capture specific dynamics of the grid. And for us, it's really clear that there is a lot of research going on in this direction to explore the consequences of imposing different assumptions on the computational complexity and the system stability of the simulation. So for us, it seems almost impossible to establish a general agreement in the same term as the IEEE 1110, but I think achieving a similar standard for inverter models, it's an important research topic for the future. For the purpose of this presentation, we use two formalization of what is slow and fast dynamics. First, I guess the standard approach that is rooted on a signal bandwidth perspective, which depicts, I guess, which type of frequency components of the phenomena are being studied. And the second approach is from a singular perturbation theory perspective, which compare between states, how fast and how slow they are. So if you go to the next slide, Jose.
So in the practical reasoning behind these transformations and simplifications comes back to the question of like, how do we actually make the simulation solvable, right? How do we actually obtain results that can be used for engineering purposes? So all of these techniques basically have like a three-step approach on like how do we want to get to a simulation that we can actually solve computationally. So the first motivation of a transformation is to basically go from a time invariant model to a time invariant one, right? So like most of the time invariant solution methods require fixed time steps. They force a huge decrease in the minimum delta t required for the simulation. So if we actually make a transformation to turn our model from time variant into time invariant, most of the time we're going to end up with a stiff time invariant model, right? Which requires an implicit scheme of solution. Now, explicit schemes of solutions actually are still expensive, not as expensive as, using a fixed time stepping on a time variant model. But then the best possible outcome is to then do further simplifications such that we can convert this, we can further simplify the hard to solving portions of the implicit model to be able to apply an explicit scheme, right? And in combination with adaptive time stepping and these solution methods, then we can actually find solutions fast, right? So if we think of a system, for example, a single line with 9 states at a discretization of 1 × -9, if we wanted to go to that level of detail, just the data of that one line will produce about 30 gigabytes worth of outputs if we were to do like a full waveform at that level of discretization, right? Which makes it clearly unmanageable even with current computational capabilities. So the best outcome again is to just basically bring down the computational complexity to an explicit model that can be integrated cheaply, and also try to get rid of like the hard to integrate portion. So like the most common approach that has been used is to basically take F and solve F, which is the devices, explicitly, and G, which is the network, in some sort of algebraic combination with partition methods.
So yeah, moving on, we sort of introduce our taxonomy first, and the initial classification of this type of domain simulation is mostly rooted on how you model the network in a quasi-static phasor simulation, or also known as time-varying phasor simulation, or I guess simply called phasor simulation. It's a simulation setup on which the network dynamics are represented algebraically, commonly using the admittance matrix relationship between voltages and current. And this type of simulation it's suited for study slow phenomena such as, I guess, inertial response, angular stability, frequency response, among others. And yeah, in specific, there is also the transient simulation here. That is a type of this quasi-static phasor simulation that is in some cases defined just as the study of the machine angle dynamics. And on the other hand, we have the electromagnetic transient simulation, just EMT simulation, I guess, that includes detailed models of all components. The network is sort of modeled with sufficient level of detail that allows to capture really fast phenomena, and I use it commonly, I guess, for overvoltage, subsynchronous resonance, converter switching, and many, many other applications. You go to the next slide. Yeah, so now sort of want to introduce some more, I guess, precise subclassification among the quasi-static phasor simulations. The main distinction here is that these new categories sort of have an additional transformation, additional assumptions on top of this algebraic representation of the network. For example, you can see that you can assume that the system is balanced, or you can include additional state that sort of model the harmonics and other things. The list includes positive sequence, RMS unbalanced, DQ0 with algebraic network, and RMS dynamic phasor. In the figure here, you can also see some tools, software, commercial, and I guess research tools that are commonly used to run these simulations, and we will talk later more in detail about each category, alternative name uses, and their main assumptions and characteristics. Go ahead, next slide.
Yeah, and so like in the case of EMT simulations, our proposed classifications include DQ0 modeling, dynamic phasor, and waveform. Of course, waveform is like the most common one type of simulation associated with the name electromagnetic transient. But in this category, there's a larger variety of approaches because it includes the possibility to go all the way down to the semiconductor modeling. And it also includes a large amount of techniques that, under some relatively reasonable assumptions, can provide some transformations and simplification that is still allowed to have an electromagnetic transient simulation, but without requiring the full extent of a waveform model. So it is important to mention that like most of the commercial development software in the simulation world has been focused on the two like highlighted blocks, the positive sequence and the waveform simulation. So for practitioners, these definitions are deeply rooted also on like which are the commercial tools available to conduct simulations. And we feel that this is one of the things that kind of limits the discussion a little bit, because of course, if you are trying to solve a model and it doesn't match reality in one software environment, your alternatives are also limited by which of the other software environments that you have at your disposal. So now we're going to start moving into the specific simplifications and transformations, and we will start talking about the most common averaging technique used in power systems, and it's dynamic phasors. So this is a funny part of the story that we were telling about when we were trying to understand the limitations and the capabilities of simulation models, because to the question, what is a dynamic phasor, we ended up with the answer that it depends. And this was interesting, and one of the most interesting discoveries in the development of this paper is that for Sanders and his co-authors, the dynamic phasors are basically, in 1991, they introduced this notion of a Fourier, the Fourier representation of an early periodic signal, where you have some narrow band multiples of a particular frequency. In this case, we use the variable bar rho. And then you can actually find all the different multipliers of the Fourier components and come up with this derivative property. So this was using the context of power electronics. So the choice of bar rho was actually the switching frequency of the power electronics, and then a different collection of dynamics that happen at different values of k that were happening, right? Now, then we suddenly figure out that there's another representation of dynamic phasors that was developed by Venkata Subramanian in his papers in 93, 94, where he introduced the notion of a dynamic phasor, which he also called the fast quasi-static phase, fast phasor. So he gave it different names, but basically his approach to develop the notion of dynamic phasors came from the linear operator perspective, that basically assumes that given a phasor of a signal, you can obtain an operator that gives you the original signal at which that phasor was referenced to. And it obtained that derivative property that we see here, which is extremely similar to the one that we see from Sanders, except that Sanders develops the derivative properties for multiple harmonic components of the Fourier series, whereas the linear operator approach finds the operation for a k equal 1, right, at what will be like a base frequency. So we're trying to harmonize a little bit the notation to explain the two versions here. And then the third approach to dynamic phasors comes from shifted frequency analysis that was developed by Martí and others at UBC. We think that between 2003 and 2005, where they formalized the concept of the dynamic phasor around the idea of the analytic signal using Hilbert transform. And as a funny note, there's a footnote in Venkata Subramanian's 1993 paper where he actually says specifically that his approach is very much motivated by the signal processing Hilbert transform approaches. So there's like a connection here between the two of them, right? So whereas Venkata Subramanian starts with a phasor and finds an operator to find the signal, shifted frequency analysis starts with the signal, applies the Hilbert transform, and obtains the phasor, right? So they're very similar to each other. This is why one of them is multiplied by EG to the bar rho, and the one is with a minus. So these three representations can be seen that all of them arrive to the same derivative property when it comes to modeling dynamic systems. So for the purposes of a time domain simulation, these dynamic phasors are now the new states of the system, right? So we go from modeling the explicit dynamics of a signal to basically modeling the average. And as an example of this elimination of the phasor derivative, you can actually you can get rid of the time variancy of a signal like ST, making it just modeling its envelope, right? So we actually propose a final we propose a definition of phasor as basically the envelope of a signal that is kind of like slightly more generic in that sense. And then, in each of these cases, the definition of phasor is basically that complex envelope, right, of the modulating frequency k rho, and it's consistent across the three definitions used. So the implication of this gives us the first insight about when dynamic phasors can or represent or should be used for representing a dynamic system, right? So the implication here is that we need a property that the integral of S of t needs to be bounded. So basically, we need to be able to calculate the Fourier series, and that for a given frequency k rho, we need to be able that the frequency, the signal we're trying to represent has to be narrow band with a particular bandwidth around the k rho, right? So this is in the case of Venkata Subramanian, is known as the one-to-one property. The case of Martí, this is a requirement for this is actually a byproduct of using the Hilbert transform on the signal. And in the case of Sanders, this is a byproduct of actually being able to find integer valued harmonic elements of the signal. So like we can figure out here under which conditions we actually have an exact transformation, right? However, dynamic phasors come with trade-offs, right? Because as you decrease the complexity of the time variancy of your model, you can also end up with larger number of states. So there is a trade-off here that hasn't been studied in detail, and it's very probably going to be like case by case dependent, where the gains that you get from simplifying the time, from going from time variant to time invariant can be diluted by, it can be diluted by the increase in the number of states, especially if the solution method is implicit, right? That normally solution methods scale with the number of states to the cube due to the cost of solving the linear system. So it isn't a silver bullet at the end of the day, but it's very good for other applications like control design or obtaining insights about the system. So one of the challenges when we were working about this is like figuring out, okay, now we understand when a signal can be represented with this dynamic phasor, but in power systems, we care about the simulation of three-phase signals, right? And one of the reasons we figured out that there was like a lot of confusion about the limitations and properties of dynamic phasors is that when you come to apply dynamic phasors to a polyphase system, there is not a unique implementation. And these limitations are going to apply differently according to the implementation used. So for instance, Venkata-Subramanian and Marti, they have implementations of the dynamic phasors on a phase by phase, right? So every single phase of a three-phase signal is converted and then used in the simulation. And in those cases, all of the limitations on dynamic phasors that we have described before apply. They need to be bandwidth limited. They need to be, very well defined. In the case of the implementation that Sander uses, we actually have for many harmonics. So for each one of the harmonics, the limitation we discuss also have to apply. But we, at the end of the day, again, we're focused on, especially at a transmission level and system-wide analysis. We care about the implementation for a three-phase signal. So an alternative approach to understand how dynamic phasors will work in the context of a full three-phase signal is applying to the full three-phase signal a space phasor simplification. So we can represent the exact same three waves as a space vector that is represented in the screen, where we can say that a three-phase signal is basically the sum of two components of a space vector with positive frequency and negative frequency components. And S plus and S minus are the dynamic phasors of that. So we left out the algebra, but basically we can then study the application of dynamic phasors to three-phase signals separately from dynamic phasors as he's been using some other applications applied to, like, let's call it single-phase signals. And the first thing that we have to note is that it is not possible to directly model an arbitrary three-phase signal with just one phasor quantity, right? Because we know that phasors don't add up directly. So like the phasor of the full three-phase signal is not equal to the sum of the phasors of the positive and the negative frequency. And so if we have, again, let's go back to the case of the line. If a line has 9 states, right? Now we're saying that for each one of those states that will be for the voltages and the currents, we end up requiring 2 phasors for each one of them, right? So we basically end up adding more and more states to the model to represent the three-phase case. Now, if the signal is balanced, and this is kind of what I call the unreasonable effectiveness of balanced three-phase signals, what we obtain when we do the simplifications is that the phasor for the three-phase signal is completely determined by the positive frequencies phasor of the of that signal. So this result is what showcases why averaging techniques are so effective when applied to balanced systems, right? The envelope of the three-phase complex signal representation is the exact same as the envelope of the three-phase signal. So in this case, we get a significant gain because we go from a signal that has 3 components to an equivalent signal that has 2 components, right? And this is kind of like a little bit of a different perspective of a cornerstone thing that we do in power systems, which is like basically like reference frame transformations, right? So as part of this, it was like, okay, there's clearly we figured out that there's clearly a connection between this notion of the three-phase dynamic phasor and the applications to reference frame transformations, right? So let's just do very quickly, we went back to understand how then reference frame transformations are used. And one of the things we realized is that the actual original reference frame transformation was implemented by Park in terms of the angles, because it was very much based on the physics elements of the synchronous machine. So like the theory, what it shows us is that the transformation from Park is actually can be done for any arbitrary signal, for any arbitrary angle, and you can go back and forth between it. However, for simulation purposes or for analysis purposes, the choice of the angle theta is what makes it more or less useful, right? So you can always do the transformation. Whether that's a useful a thing to do or not, that's a different story. So, and here we just like then figure out like there's a connection here. If for certain implementations of the transformation of Park, then the Park transform is a phasor and it's an exact phasor transformation of a balanced three-phase signal. Right, so in simulation models, the things like the calculation of theta t is done like when we're now into the simulation. If we do it by integrating like the frequency, right? So it starts with a question of like, okay, we're integrating the frequency, but then what is the frequency of the system, right? And the definition of this part transform in terms of the frequency is effective in terms of a simulation if we assume or we think on if we choose this frequency to be the same as a system frequency omega s, and then we assume that that system frequency is relative is constant over time. So like again, the results of the transformation don't change with the choice of theta, but the effectiveness of that transformation as it applied to simplifying a simulation, which is what we care about at the end of the day, very much relies on this choice. So if we can take it one step forward and start asking ourselves, what is then the system frequency? What is the role of the system frequency in these transformations? If we saw the dynamic phasor very much rely on a bandwidth limitation aspect, and we have to choose this bar row to figure out if it's valid or not. But when it's applied to three-phase system, we actually can get rid of the omega f component because the transformation from reference frame to reference frame pretty much relies only on the delta omega being the delta omega of the rotor when you have a machine. And in fact, the system frequency is not even a model quantity in a simulation, right? So, and this is a topic that next week's UNIFI speaker has discussed a lot in his papers, Professor Milano. So I'm not going to go into many details here, but for the purpose of simulation, we realized, okay, the system frequency is actually not a model quantity, and it could be arbitrarily chosen most generally, but for the purpose of making a simulation more solvable, certain choices makes more sense than another. Now, when we go to IBRs, now things change a lot, right? Because in the world of the machines, you can make these reference phase transformations by having this local delta omega r to make the transformation. And actually, DeMarco, in an early paper about dynamic phasors on 1901, he actually calls that the synchronous machine the perfect demodulator of a three-phase signal, right? And it's like a really funny way of putting it around, because it means that the fact that the machine is rotating and is rotating at its own frequency allows it to demodulate any three-phase signal that exists in the system. But in the case of an IBR, the relationship of the ABR with respect to the system frequency is pretty much governed not by a rotating mass equations of physics, but also how but it is dominated by how the controls are configured, right? And there's many proposals of different configurations. There's people who want to get rid of the PLL. We should have it or not have it. And there's like the droop or not the droop or virtual synchronous machine, etc. And this creates, like, from the simulation perspective, a problem that heretofore hasn't been an issue at all, which is that we need to model how the frequency measurement of these controls is actually measuring the frequency. But like it becomes a very different question, because then like we need to rely the equation that is most regularly used to simulate this measurement of the frequency is the one we see in the screen, that then relies on a network being in a particular reference frame. That again, in the course of the machine, we just saw that we can get rid of the frequency and the frequency deviations. And we have these BQ and BD terms. And the implication is that if we mischaracterize or if we simplify too much the frequency dynamics that exist within the voltage quantities in the system, we end up not just simplifying the simulation, but we can end up mischaracterizing the effects of those frequency deviations on the controls, right? And that's a critical change that happens now, because now some assumptions that had relatively low impact in the case of machines, given the existence of the rotor equations and its own local demodulator, now can have significant impacts in the quality or in the precision of the simulation that we get in the case of IBRs.
Yeah, so now I want to talk about another approach for simplification, specific how singular perturbation theory has been using in modeling and simulation in power systems. So if you go to the next slide. Yeah, so typically simplifications, I guess, in power systems relies on practical knowledge of the physical system that justify, I guess, neglecting certain dynamics or ignoring certain parameters, or in general imposing some arbitrary assumption that are indeed helpful for accelerating simulations. And in many cases, this simplification that has been proposed have been properly formalized using time-scale separation arguments derived from singular perturbation theory. So commonly presented in literature, you will see two types of state variables in this topic, denoted as slow and fast, in here with the subscript S and F. The presentation of this topic also includes this real parameter epsilon that is usually really small and is used to describe how much faster the fast dynamics are in terms of the slow dynamics. So if we set this epsilon to 0, we can treat the fast dynamics as algebraic equations, and basically using singular perturbation theory and studying the so-called boundary layer system, we can properly argue the convergence of these fast dynamics into a root in some specific time window. So for a time simulation perspective, eliminating these dynamics provides significant benefits in reducing the stiffness of a system of differential equation, and of course, eliminating these states via substitution implies that you have less states. If you can do that, that of course is useful for accelerating accelerations. For us in practice, singular perturbation theory is the theoretical justification for the elimination of some system dynamics, such as, I guess, network current or stator fluxes typically used, for example, and providing guarantees that these simplified representations, for example, the admittance matrix model between voltages and currents, is a reasonable approximation of these other dynamics. If you go to the next slide. Yeah, so as mentioned, I guess at the beginning, the inclusion of network dynamics is a crucial distinction of our proposed simulation taxonomy, right? So for this presentation, I will introduce an example of how we can use transformation and simplifications in network modeling to achieve different simulation types. Just to clarify, similar approaches for model reduction can be used for inverters and machines, and have been using if you sort of go to the literature. So in the case of network modeling for transmission system, the main effort it's in properly modeling transmission lines. And it is well known that sort of this implies using a distributed parameter model that involves partial differential equations that of course are quite difficult to include in large simulation models, of course. So the experience, and for many authors, has shown that the effects of using simplifying models are not as significant if you compare of using the distributed parameter models. But in general, the simplifying assumption for transmission line modeling, it's on the line length. For churn lines, usually it's common to assume that you don't need to model the shunt components. So the distributed parameter exactly reduced to an RL circuit. Another approach is sort of assuming there is a lossless line, and this sort of results, the distributed parameter results in a two-port system that has a time delay. And the inclusion sort of a lumped resistance in this model results in this famous Bergeron model that is commonly used in waveform simulation. Finally, the lumped pi model that it's mostly used is obtaining by assuming from the distributed parameter model that is driven for a sinusoidal wave as a constant frequency. So this usage of lumped pi model as like a circuit differential equation, it's indeed just an approximation of the partial differential equation in a time domain simulation. So of course you have to be careful because their accuracy will depend on which type of thing you're modeling and the line parameters that you have. Yeah, so you go to the next slide. So yeah, this is sort of the example that I want to introduce. I present a line as a lumped pi model with some differential equation representation in per unit that can be used in a waveform simulation model. The numerical integration substitution was most likely will be used here using the trapezoidal rule to include these equations in the simulation. And I just want to highlight that the currents I1 and I2 that are sort of driving this line most likely come from another dynamical system. And this will sort of have a sinusoidal form that will include the term sine of t. So this is what will make the system of differential equations time varying. Just to note, these are 9 differential equations just to model a single line in this waveform time simulation. Yeah, if you go to the next slide. Yeah, so one approach is to using this part transformation using a constant frequency to write, I guess, this model in a DQ0 coordinate system. If you assume that the system is balanced and the network is symmetric, we can eliminate the 0 coordinate, so we end up with this sort of representation. In addition, if sort of the currents I1 and I2 are properly transformed, of course, representing this DQ reference frame, then the system of equation will end up being time invariant. In here, of course, I'm assuming that these signals does not have harmonics. So if you do the parse transform, you end up with a time invariant system of equations. In the other case that you have harmonics or the system is not symmetric, then there will appear some other time varying terms that sort of will dilute many of the computational benefits of this transformation. So with these assumptions, at the end, you end up with 6 differential equations that are time invariant. I only present 3 here, but yeah, the real and imaginary part are usually split that give you the 6 equations. So if you go to the next slide. So finally, as a final step, you can use singular perturbation theory to get rid of the left-hand side of the equation, because this term L over omega b or C over omega b are quite small in 50 or 60 hertz systems. So yeah, singular perturbation theory provides a good avenue to eliminating these dynamics. And what happened here is that you end up from the original waveform model with a relationship between voltages and current that is just algebraic, and it's based on the admittance matrix representation. So these steps actually results in the same network formulation that is used in positive sequence simulations, in which the DQ components are sort of match the real and imaginary part of the positive sequence phasor. So just as sort of an additional note, it's important to be sort of aware that when you use singular perturbation theory to reduce network dynamics, you have to consider what are your, I guess, speed or how fast are your device models to ensure consistency between the equations that you're using. For example, it's common that when you eliminate line dynamics, you should also eliminate the stator fluxes in machine models, and those are in similar time scales. Yeah, if you go to the next slide. And yeah, and just to sort of conclude here, the issue with singular perturbation theory is not easily generalizable. So the example here provides it's a virtual synchronous inverter model connected to an infinite bus, and we're doing a perturbation. It's easily the dynamic line rapidly converts to the algebraic representation, but there is plenty of literature that sort of showcase how the elimination of these line dynamics can enlarge the stability region of grid-forming inverters, especially for tuning outer controllers. So that sort of give us a false sense of security of how safe we're operating. So sadly, these techniques sort of need to be assessed case by case. So if you go to the next slide. Yeah, and to conclude the presentation, I'll go in more detail to the proposed classification here. Just recall that we have this, I guess, partition between quasi-static phasor and electromagnetic phasor, and the main characteristic of the quasi-static phasor is that we have the network as an algebraic representation. So if you go to the next slide. Yeah, so I guess first I want to sort of, in the classification, I want to talk about positive sequence simulation. This is by far the most popular approach using for running these simulations. The key assumption, as I mentioned, is that the network has to be balanced, only if the positive sequence is modeled. In the literature, you can find that it's called RMS balance, electromechanical simulation, transient stability simulation. Yeah, these last two names don't necessarily imply that the network is balanced, but it's commonly used like that. And there are it is pretty well developed the simulation tools available here. The next in the list is RMS and ballast simulations, and which the network is still obviously as an algebraic representation, but you model the network in symmetrical components, then you perform some type of fault. And the common approach is sort of simplify depending on the faults to get to, I guess, it's usually get to a single phase representation at the end. The DQ0 model with algebraic network, it's again, is the same, that's positive sequence if you have a balanced network, but the way it handles unbalance is that it will appear sort of time varying characteristics. So it's sort of a research approach that it's sort of being investigated right now. And just to conclude, the RMS approach is the same as the dynamic phasor approach. You just ignore the left-hand side of the network equations. But the important part here in the phasor and the dynamic phasor approach is that you can have multiple states for different harmonics. But yeah, more sort of will be in the next category.
So the next category, of course, is the an EMP category, right? And in this case, the waveform simulation is also known as point of wave, ABC, are all the names that it has, is the most developed one, right? Like there's a lot of very specialized algorithms that come from the Domo method of representation of the dynamics. And it's also the most comprehensive because it allows the modeler to choose between a large array of different dynamics that could be included, right? So you can go all the way down to like the switching dynamics, which requires some specialized algorithm for reinitialization of the dynamic state, and it actually can have certain simplifications. So the important here is that the network, generally speaking, is modeled as a set of dynamics equations, still with simplification, right? As Rodrigo mentioned, the general theory of the network is a bunch of PDEs that are really difficult to solve. So we still use simplification, like the Bergeron method or even the long parameter method is still available within these type of simulations. But the challenge of these type of simulations is that, again, they generate also a lot of low quality information, right? Like one of the things that it happens is like sometimes the dynamics of the system don't require us doing the sampling of all of the 60 hertz or at 600 hertz and so on. Like you don't need to have all the detailed ABC signals to actually obtain information about the dynamics of the system. And again, a lot of the software is very mature. It uses the numerical integration substitution, and it has, we think, and it's, the challenge that it has is that it's a type of solution method that is difficult to initialize. If you look online, there's a lot of different challenges about how do you transform a device from one type to the other, because at the end of the day, it's using still a time invariant model on the background, right? So it's a fixed step, generates a lot of information, but it's very detailed in its capabilities. Now, we have decided to include DQ0 modeling, also known as this fast time varying phasor, as an EMT model, right? And again, we can apply the DQ0 transform, and maybe the model will still be time invariant. The model will be time variant, but it will be a time variancy at a much higher frequency, so you can still decrease the delta t. But again, like the critical thing that we want to achieve is that in the case of balanced systems, there's enough evidence that if you're analyzing the controls and designing and studying systems in balanced conditions, the DQ0 model, with including all the dynamics of the network, again, in the cases where the dynamic model of the network matches between a full waveform and DQ0, the results are one-to-one. So, and that's a strong conclusion for us, because we basically are trying to say, if we actually start wanting to study IBRs and systems with a lot of renewable resources that are grid forming, and we're finding out that the boundary limitations and the effects of the simplification signal perturbation theory gives the results that are not necessarily stable, the application of a dynamic DQ0 model could be a solution to that kind of thing. And finally, the last implementation that we have is the dynamic phasors, as implemented by Seth Sanders originally. And of course, there's a challenge here because you need to define very clearly for the dynamics and the behaviors that you want to include how many harmonic components do you want, right? So again, this is where you know, a lot of researchers are looking into this to basically say, what if we include a particular number K of components to be able to model multiple frequencies and multiple effects? One of the things that I wanted to mention before going to one of the final slides is that the critical thing that makes the decision in the case of EMT about the simplifications and the transformations that we can use, at the end of the day, have to do with the fact that this is a system-wide simulation, right? There's a lot of theory and a lot of analysis when you come to like the EMT simulation of devices, but in the case of the system level, one of the important aspects is whether some of these how much energy is actually being transacted, so to speak, across the system, and how much these simplifications actually affect that energy balance, right? And in that sense, simplifications like using a reduced number of harmonics or using DQ0 model can still be representative for engineering purposes of the state of the system beyond the quasi-steady state assumption.
Yeah, and I guess this is just some sort of summary. So I think given the time, we should skip this just to the conclusions, Jose, probably.
Okay.
Yes.
So the conclusions at the end of the day are like, you know, phasor transformations, regarding the implementation, they do enable cheaper time domain simulations than full waveform. And the limitation need to be taken into account, need to be considered carefully. Like the fact that a phasor transformation might actually not match the requirements for an exact transformation doesn't mean that it shouldn't be used. We just have to understand the limitations on those conditions. Quasi-static phasor simplifications are not as general as have been used in the past in the presence of IBRs, because, you know, standards like 1110 and like over 100 years of experience with electrical machines allows us to know better that stator fluxes and machine and line dynamics are about the same range. And again, there's a large number of theories from the 90s from Picsauer and Professor Venkatasuramenyan that actually shows that if a system is stable under a quasi-static state assumption, might actually not be stable under a full dynamic assumption. So like you cannot prove stability in the other direction from the simplified to the general, but just from the general to the simplified. And at the end of the day, we find that a huge limitation in the availability and understanding of these techniques is the fact that commercial softwares have been developed for two types mostly of simulations. And that kind of hinders the exploration of new alternatives, because when you want to scale up analysis, like if you actually want to do a WEG size system, or you actually want to study systems at the scale that ISOs and the scale that developers actually need to do, the limitations of the existence of these two tools can actually limit how this exploration is done for these other alternatives. So thank you very much. And
thank you.
Yeah.
That's it.
That's it.
Okay, thank you. We'll go ahead and stop recording.